Okay.
Was I supposed to get a notice that it's recording?
I think it's recording. All right. Welcome to the last Compass lecture of the semester. Our speaker today is Kyla. She's a PhD student in the Department of Earth and Planetary Science here at UC Berkeley. She also completed her undergraduate degrees here at UC Berkeley in chemistry and planetary science. Her research focuses on studying the properties of planetary materials under the high temperatures and pressures found in planetary interiors using atomistic simulations. She particularly focuses on studying properties of planetary ices, mixtures of ammonia, water, and methane, with hopes of advancing our knowledge of the structure of the ice giant planets Uranus and Neptune. So let's welcome our speaker.
Excellent. Thank you for the introduction. Thank you for the invitation. This is very cool. So I think that he just gave like an excellent summary of probably my entire talk. I probably should have thought about what I put in the bio. But so my talk I have called Mysterious Magnetic Fields, Machine Learning, and NASA's newest flagship mission, exploring the deep interiors of Uranus and Neptune. I tried to think of a title that would attract me to come to this talk if I was an undergrad. It does not appear I was too successful, but that's okay. This is the last day of classes. If I was an undergrad, I would definitely not be in this room right now. So yeah, to introduce, this is not working. Oh, there we go. To introduce myself again, I'm a first-year PhD student in the EPS department. I also was an undergrad here at Berkeley. I studied chemistry and planetary science. For any undergrads in the room or anyone otherwise, feel free to reach out to me about anything after this, particularly like academics, research, grad school decisions, anything like this. For the undergrads present, I was asked to briefly go through my academic journey that led me to doing a PhD in earth science, which goes as follows. I actually came here to Berkeley as a freshman when I was 17, intending to study astrophysics. Clearly that was not the path I actually chose. I loved astro, but I think at the time I had a lot of trouble like finding community. I think a lot of first-year students come here and find themselves a bit overwhelmed and not really sure what's going on with life. So I actually left the university for a few years after my first year and got married and adopted a bunch of cats and took community college classes. And then like eventually got it together and came back. And I studied chemistry because I thought at the time that was more the direction I wanted to go. And I tried research there. I did research in nanoparticles, but I never really found something in chemistry that clicked. You know, that thing of like, oh, this is definitely what I want to spend my career studying. But I did really miss geosciences, like astronomy and planetary science. So I started taking some like earth science classes, really validated my decision because I loved it. But I was still curious, like, how can I apply my chemistry degree to this? So I started doing research in geochemistry, studying like how to extract rare earth elements from fly ash, which is like the inorganic byproduct of burning coal, which is produced in enormous volumes all over the world. And then there was this thing that happened in early 2020 where undergrads couldn't get into research labs for a really long time. So I ended up taking up a different project in like chemical modeling. It's very exciting. I bring this up because we just submitted the paper this week for my senior thesis. And also because we couldn't get into like instructional labs in chemistry because of the pandemic, the department started offering a bunch of really interesting computational classes. So I took one and totally fell in love with computational chemistry. And so when I graduated, I asked a professor in the EPS department, Burkhard Molitzer, if I could do a summer project with him, because luckily he did computational chemistry or physics. My group mates might argue about this, applied to planetary science. And so I ended up working with him for the entire year after I graduated, which was amazing, and ultimately decided to stick around here at Berkeley to do my PhD in his group. So that is where we find ourselves today, and this is the end of my first year, and it's been awesome. So again, I think we might have like one undergrad in attendance, but here are my tips for you. The community wants you to succeed. I think that if I had internalized this more when I was 17 or 18 or 20, I would have had a much better time about it. I think this manifests in how you interact with your community. Like, reach out for help if you need it. early often. This is my first semester as a GSI, and I think I never really understood before that how much your GSIs and professors and course staff and department staff and, you know, college staff really want you to succeed and will be there for anything you need. Ask for opportunities if you need it. Things like asking for research, internships, like a lot of opportunities you want are kind of invented because you ask. And also study for STEM classes and groups. I would have done better in quantum mechanics if I'd done this. And also to type this new program MPS is doing. If you're not part of this, you should totally join. It's called MPS Scholars. I wish something like this was around when I was an undergrad. They have like community building, mentoring, lots of resources. They fund summer research for undergrads. So a lot of amazing things going on there, and it's very new. So give it a try. Okay, more to science, which I think is why you all actually came. Here's our summary. I will talk a little bit about our solar system and the story of Voyager II, which, as we will discuss, was the first and only spacecraft to ever visit Uranus and Neptune. Then we'll get into planetary magnetic fields and the assumptions that we make about the interiors of Uranus and Neptune based on what we observe. A little bit about how we study planetary interiors using high pressure simulations, including very recently, machine learning is becoming popular. And then we'll end with talking about NASA's next planned flagship mission, which will be the first dedicated mission to Uranus. Okay, so this is our solar system. I'm going to scoot this over a little bit. Maybe that's better. So this is our solar system. You're probably all familiar with it, but I want you to note a few things. The planetary sizes are actually to scale. The planetary radii, or like the distance between them, is not. So like, for example, the distance between the sun and Earth, Saturn should be 10 times as far away, not like 2 to 3. And like Neptune should be like 30 times far away. So in reality, our solar system is very empty and there's incredible distances between the stars. Ceres is a dwarf planet that lives in an unpictured asteroid belt between Mars and Jupiter. And of course, Pluto has, in our lifetimes, been demoted to dwarf planet because it is also living in a giant asteroid belt called the Kuiper Belt that is past Neptune. And it's interesting because the history of humans exploring our solar system is actually very, very modern, which I think maybe our generation hasn't fully internalized in the way that like our grandparents did. But like after World War II, the US and the Soviet Union were in a Cold War, which manifested in a lot of ways in competition for technological innovation. And so in 1957, USSR launched Sputnik 1, which was like the first body in the solar system. It was like the first human spacecraft to be able to orbit around the Earth. And of course, this made the US like really mad. And so they had to kind of like stomp the USSR space program, which I'd say we did pretty successfully because NASA was founded the following year. And then within 4 short years, the first spacecraft to ever visit another planet, Mariner 2, visited Venus. And then like in the course of the next, I think like 21 years from when NASA was founded, Venus, Mars, the Moon, Mercury, Jupiter, and Saturn were all visited for the first time by US spacecraft. So like I find it kind of fascinating how quickly like the space race exploded. And I do want to emphasize these were all flybys. None of these went into orbit because that takes a lot more, that's a lot harder to do. And so it actually requires a much longer flight time. So like reaching Jupiter and Saturn was a huge milestone because they're quite far away. Like Saturn is 10 times as far away from the Earth as, not 10 times as far away from the sun as the Earth is. So then reaching Uranus and Neptune was like a much loftier and more time-consuming goal because these planets are so much farther away still. Again, Uranus is like 15 times as far away, and Neptune is like 30 times as far away. So, but in the 70s and 80s, something really special was happening, which was that for the first time in 175 years, this happens on a 175-year cycle, the outermost planets, Jupiter, Saturn, Uranus, and Neptune, were going to be roughly aligned relative to Earth. And so NASA started the Voyager I and Voyager II missions with the goal of being able to use a single spacecraft to fly by many planets at once. And so Voyager 1 in white was launched in 77 and passed Jupiter and Saturn in 79 and 80. And Voyager 2, funnily enough, launched about 2 weeks before Voyager 1, was able to pass Jupiter, Saturn, and then onto Uranus and Neptune. And so the Voyager 2 was the first spacecraft to ever pass these planets, and to this point is the only one to have ever done so. I thought you might enjoy seeing a video. Voyager 2 is in purple of how it passed all of these planets at one time. And note that it makes use of all of the locations of the other planets to bend its trajectory, which is a process called gravity assist or a slingshot maneuver. And after visiting these planets, Voyager 1 and Voyager 2 just like continued deep out into the solar system. NASA is actually still in like radio communication with both of these spacecraft today. And you can go look up like on a daily basis where they are and how far they've gone, which I think is pretty fun. Maybe somewhat sentimental. These spacecraft were expected to go like very far out into the solar system and eventually into the galaxy. And so they were actually both equipped with what was called the Golden Record, which had really popular cultural music and was inscribed with these like beautiful scientific and cultural diagrams. So the idea was like if an alien, like intellectual alien race ever found these, this is like what we want them to know about humanity. That's pretty cool. Yeah. That's a good question. I think so, but I'm not actually certain. They're called like the Golden Record, so I'm going to assume so. Oh, they are made of gold? Oh, fantastic. Thank you. But so of interest to us, as I mentioned, Voyager 2 was the first to visit Uranus and Neptune in 1986 and 1989. So it took these photos, and it spent about 48 hours passing each of these planets, enough to like, when it was close enough to actually collect the data. 48 hours only, and this was the last time the spacecraft had ever been visited, like 35 years ago. So Voyager 2 collected a lot of data, but one of its main goals was to study the magnetic fields of the planets that it passed. Just to remind you, a magnetic field is like a region around an object, in this case planets, where charged particles are moved by magnetic fields or like by a magnetic force. So we'll often see these visualized as like concentric lines, like entering one side of an object and exiting another. And all of the planets in our solar system, which have magnetic fields, as far as they knew at the time, were dipolar. So like they had a north and a south pole, field lines like and exiting one way and entering the other. Something like Earth, Jupiter, Mercury, Saturn, all look like this. Note that Earth and Jupiter both have their magnetic fields like slightly off from their axes of rotation, which is why it looks a little bit funky like that, but like still dipolar magnetic fields. So like I was just saying, these are typically aligned or close to like the rotation axis of a planet. And so broadly speaking, magnetic fields are generated because you have like convection of charged materials like deep in a planet's interior. So like convection is the process of which like hot material rises, cold material sinks, and it creates these circular cells of material moving. And if this material is charged, then you get a magnetic field. And so for Earth, this happens in the liquid iron outer core. As expected that like other rocky planets that also have magnetic fields, it's formed in the same way. The gas giants Saturn and Jupiter also both have dipolar magnetic fields. Like here's a picture of Jupiter with kind of its like magnetic field lobes. But it does go all the way around. It's more of like a torus. So this is like a slice. So you can actually visualize the two lobes. But for gas giants, the magnetic field is still generated by convection deep in the planet. But for gas giants, it's not in like molten iron, it's actually in metallic hydrogen. So knowing that all previously explored planetary bodies, Earth, Jupiter, Saturn, Venus, had these magnetic fields, you can understand how confused scientists were in the 1980s when they got data back from Uranus and Neptune, and it looked like this. These are not dipolar magnetic fields, and these were the first kind of planetary bodies that had ever been observed to not have dipolar magnetic fields, if they did indeed have a magnetic field. So these are not dipolar, they're not aligned with the rotation axis, they're more like quadrupolar. So to understand this, you have to kind of review what we think ice giants are structured like. So from their density, which we know because we know their mass and their size, like their radius, and we can guess their mass from like interactions with their moons, we can infer that these planets do have a significant amount of ice. So I want to address a misnomer here because it kind of drives me crazy. These planets are not actually cold. They're called the ice giants. It's not a good name. These planets really are not cold except for like at the top of their atmosphere. Like by the time you're at the bottom of the atmosphere, it's already pretty hot. By the time you're deep in the interior, it's as hot or hotter than Earth's core. So they're called ice giants because they're made of a series of materials that we call the planetary ices. Primarily like water, methane, and ammonia, but also like sulfur dioxide, maybe carbon dioxide can be included in this, and in this grouping of planetary ices. And like indeed, when the planet was forming, like, and these were just like molecules or rocks out in space, like yes, they were cold and solid, which I think meets our like Earth definition of ice. But now that they're in the planet, we still call them ices, even though they're quite hot. So for example, these are likely solid, but like very, very hot in the planet interiors. Anyway, so it is proposed that Uranus and Neptune will have a small core that's made of rock and iron. And then they do have the same thick helium hydrogen atmosphere that the gas giants do. And by the way, these look blue because they have a tiny bit of methane, like a very small fraction of methane in the atmosphere, but that's why they're blue. But then this really thick middle region, what we might call the mantle, is primarily planetary ices. And so going back to magnetic fields, I said that we have to generate magnetic fields by convection. So if Uranus and Neptune have different magnetic fields than the other planets, then they have to have a different region of the planet convecting. So this is like a simple profile of Uranus and Neptune. Like this is the rocky core. The atmosphere is not shown. So all of this is like the mantle that I was just talking about. So like this region. So our best guess now is that the mantle of these ice giants breaks up into layers, at least two. So you'll have this really thin upper layer where the convection is happening, and then you have this lower layer where it is not convecting. It's either a liquid that's stably stratified or it's a solid. But so convection only happens like close to the surface of the planet, maybe like the top like 25% in terms of radius. And like modeling and simulations using this structure have been able to recreate roughly the magnetic fields that were observed for Uranus and Neptune. So like this is the planetary science community's best guess right now as to what Uranus and Neptune look like. Like to be honest, this mantle separation that likely occurs, I think brings up more questions than it answers. Like, why would the planet do this? Why would it break into layers like this? There's kind of two main ways this could happen. First, it could just be different materials that are not miscible, which means like able to mix. So think like on Earth, water and oil will not mix. Like given enough time, you'll have a layer of water and then above it a layer of oil. So something like that could be happening at this boundary. Or the second thing is that it could be the same material that undergoes a phase change. So again, think on like Earth, you have lakes that get really cold and then you get an ice layer on top and water below. On most materials, this would not happen. Water is really interesting because ice is less dense than liquid. Most materials is the reverse. The solid is more dense than liquid. So that could be what's happening here. Is it's the same material, just you have a phase change because remember, as you get deeper, the pressure and temperature increases. And so you could encounter a point where, the material transitions to a new phase. Another question is that, is the material in this top layer convecting enough, or is it conducting enough to actually create the magnetic fields that are shown? Because like there's two parts of the magnetic field equation. It has to be convecting, it has to be doing the circular motion, but it also has to be able to carry charge, which is how the magnetic field is generated. Like, is this material actually conducting enough? And then the third question is this bottom phase layer of the planetary ices visualized in blue, is it like what is it? Like, is it solid? Is it liquid? Does it conduct? Does it not conduct? Because there were several different combinations. Sabine Stanley did this paper when she was in grad school, which is really quite famous on Uranus and Neptune magnetic fields. And their work found that there were several different combinations of like phase and conducting or non-conducting that could make this magnetic field setup work. So it's quite unclear like exactly what this material is. And so these are all questions that we aim to answer by studying how materials will behave at extreme temperatures and pressures like planetary interiors. So many scientists work on experimental methods to study things like this. Like one popular method is what's called a diamond anvil cell. So this is you stick a sample of your material you want to study between two diamonds, super hard material, and then you compress it from both directions. And if you are so inclined, you can also heat it at the same time. And from there, you can study the properties of the material. But I think these do not go up to super high pressures. Okay, so another method is just to use giant lasers to compress and heat the materials. So some of the biggest lasers in the world are used for this application. So shown here is the National Ignition Facility, NIF, at Lawrence Livermore National Lab, which is about 40 miles from here. And this is used for, amongst other things, studying materials of planetary ices. But if you heard a lot of news recently about like a nuclear fusion breakthrough, this is where that happened. But experimental methods can be slow and really expensive. I think shots on the NIF, I was told, cost something like $1 million each, and they can only do a few a day. And the results can also be a little bit ambiguous and time consuming to interpret. And also, you can only go up to certain temperatures and pressures reliably like this. And so this is where computational work comes in. And this is what my research group, working with Professor Melitzer in the EPS department does. So we study how materials behave at extreme temperatures and pressures using supercomputers. So this is NERSC's Perlmutter. NERSC is at Lawrence Berkeley National Labs. So just right up the hill. And you'll notice this computer is roughly the size of this room. So it contains many smaller computers that we call nodes. And you can use like one node, or you can combine multiple depending on how much computer power you need. But like even a single node has many times the computing power of like an average or even good personal computer. And so supercomputers like this exist all over the world, but we're very lucky to have such a modern, powerful one accessible to our group. And so specifically what we do, I would call atomistic simulations. Some might call like ab initio simulations. But so like to review what we mean by simulation, a simulation is when you're trying to imitate like a real world process. And for atomistic simulations, we try and imitate the behavior of materials, specifically groups of atoms, using computers. Like this is a basic process. You would prepare a cell of atoms of a specific material, of a specific symmetry. So this is a simulation I ran quite a while back of a superconducting compound, carbon, sulfur, hydrogen, which has been involved in kind of a controversy about whether or not this is actually superconducting, or there was clever forgeries by the authors. But anyway, this was a Nature paper, and at the time, it was thought to be like the highest temperature superconductor ever discovered. Anyway, but when you talk about solids, like the atoms will have set arrangements with each other, which we call the symmetry. And I think we're familiar with this, just thinking of like water or carbon dioxide. Like there's a reason that water has bent angles and carbon dioxide is linear. And so this is symmetry, but then you would think of it in like an infinitely repeating solid. So you prepare a box of these atoms, and then you heat it and pressurize it to your desired specifications. And then there's so many things that you can study. And of course, you tune the simulation parameters depending on what you want to learn. So things like, how do the atoms move? What's the energy of the system? What is the phase? So like liquid, solid, gas, probably not gas, our group does too high pressure, but different materials mix. And then if you were to change the temperature and pressure, do any of the answers to the above questions change? And then once you understand a lot about the material, you can try and answer questions of like, what could this tell us about planetary interiors, or superconductors, or how to achieve nuclear fusion? So here's a series of simulations that I ran, and you can kind of see what I'm talking about how things change once you change certain conditions. So on the top is the temperature I exposed all of them to. To the far left, this is a solid, as evidenced by the fact that the lattice of all of the atoms is like maintaining its form. You will notice them vibrating, and this is indeed what solids do, even at room temperature, but nothing is diffusing, it's not melting. On the far right, however, is a liquid, as evidenced by the fact that the lattice structure has completely fallen apart, lost all regularity, and that things are diffusing fairly rapidly. And in the middle is an interesting phase, which I'll talk about more in a little while, but it's called the superionic phase. And so this is one in which you heat it to a point that the heavier atoms still cannot move, but the lightest atoms, namely hydrogen, start to diffuse through the cell like a liquid. So it's very interesting, like mixed liquid solid phase. So each of these simulations I just showed you, I spent about 5 to 10 hours running using 4 nodes that all had 68 cores. I think my computer is a fairly nice one and has 8 cores. So I tell you this to illustrate how much computer time stuff like this takes to do it accurately. And the reason these simulations take so long is because they're doing like very precise calculations. So I keep talking about how atoms move. I really mean nuclei. So if we want to understand how nuclei move, we need to understand like how the electrons are distributed around them, and how the interactions of each nucleus with all other electrons and nuclei create forces and make them move. But it's a little bit more complicated than this diagram on the left. And part of that is because electrons are not, pinpoints as we often like to regard them. They're actually much more like probability clouds. And depending on like the energy of the electron, they will have different shapes. And they will have different probabilities of being in space, depending on like distance from the center. Like modeling electrons realistically can be quite computationally intensive. Or what we might call in like computational work, like expensive, like taking a lot of like both computer time and real world time to actually accurately model. Luckily, we do have a significant workaround for this, which is called density functional theory, for which Walter Kohn won the Nobel Prize in 1998. So the basic idea is that instead of calculating the interactions of each electron with every other electron and with all the ions, you can kind of abstract the electrons as a cloud of varying density. And then you can determine the forces on the nuclei based on the local density of that cloud. And of course, there's increasingly accurate and detailed models regarding working with this like electron cloud, but then those do get more computationally expensive. And so while this is still like, while this incredibly speeds things up, we're still limited to running simulations of like maybe like 400 atoms. Most of what we do is more like 100 to 150 and like maybe 100 picoseconds. So I think if I ran a simulation that long, my advisor would tell me I was wasting computer time. So like really more like 10 picoseconds. So 10 picoseconds is like 10 to the negative 11 seconds. So as accurate as we try and be, we're only able to capture very small systems for very short periods of time, which is where the community is hoping that machine learning can fill that gap. And it's kind of an amazing time to be in computational science in any field. It's a good time to be a young scientist in computational work, because I think in our lifetimes, like machine learning is going to really transform how we do simulations. I mean, you've probably heard this term, but to define it for you, machine learning is like in simplest terms, just a process in which computers learn patterns from pre-existing data. And I mean, there are quite complicated methods to do this, but foremost machine learning is just statistical analysis. And it turns out computers are often really good at discerning patterns in data that humans cannot pick up, or that requires way, way too much data analysis that humans would ever actually be able to pick the patterns out. So there's a lot of methods to do this. One really popular one, and the one that I use in my research, is called neural networks. And to be honest, I think explaining in detail how neural networks work is probably outside the scope of this talk. But the basic idea is that, like in data analysis, you expect causations. Like if you have like a 10-pound pointy-eared mammal, it's probably a cat. Or if like it's really darkly cloudy outside and it's really windy, it's probably about to rain. Like, as humans, we understand causation, but it can often be much harder to see in gigantic data sets. And so this is where a neural network comes in. You train them. And so this means you feed them kind of on one end, like your input data, and then you feed them kind of from the other end, your output data, and it's able to optimize statistical weights in the middle. And so that in the future, when you feed it input data, it's good at predicting the output. So like I was just saying, machine learning is becoming very popular because it can be used to predict behavior. It's even being used widely to predict like human behavior. For example, like a lot of banks are starting to use stuff like this to predict, for example, like how likely is someone to default on their loan based on their income and their previous loan behavior and like their age and whether they're married. Like they will take in tons of data about people and tons of historical data of how people who have taken loans end up using or defaulting on those loans to be able to say like, you know, X% of people that meet these characteristics will default on their loan and like make decisions based on that. So it's really interesting. But of course we use it for atomistic simulations. The idea is that if you can train what's called a machine learning potential, then you can calculate how nuclei move and what the energy of the system is using much, much less computer time than computational methods, or like traditional computational methods. The basic process is as follows. You have to generate some data using the really expensive method. So you have to be able to say, you know, we have a number of different data sets that we know like where the nuclei are and then what the energy and forces in the system are. But then you would train a neural network on that. And it says interpolation because really this is just like the statistical analysis portion. It you know, adjusts the weights of the neural network so that when you feed it atomic nuclei positions, it outputs the energies and forces. And in doing so, it trains what's called like a potential energy surface. This is basically like a very mini dimensional understanding of like, if atoms are in certain positions, then the energy of the system and the forces on the atoms are going to be this. And they can be quite accurate. And so the last part is that you can apply this. And so this, if you have a well-trained neural network, then you can predict energies, forces, a lot of other stuff about the system without having to do this very, very expensive calculation of the electronic structure. You basically skip all of this very time-consuming like electronic analysis. So when used for simulations, machine learning can be like orders of magnitude faster. This was a plot I made for a grant. We still haven't found out if we got the grant or not. But so if you're using like traditional ab initio methods, you're stuck to like picoseconds. So think like 10 to the negative 12. You can go like 1,000 times longer, or you could go like many, many orders of magnitude more atoms because it takes so much less time that you're enabled to run for so much longer and so much bigger systems. And so this can be really important because there's like material behaviors that do not happen on the time or size scales that we can study with traditional DFT methods. So I think one thing that my groupmate in the audience was trying to study was like material defects, which only arise when you can study for longer and bigger systems. So I think that some point in the future, our machine learning is going to get so good that you really will be able to connect like atomistic behaviors, like macroscopic scale things. We'll see. Okay, so my research specifically has been studying superionic properties of what we call HCNO compounds at the interior conditions of ice giants. So we call them HCNO compounds because this is really what they're composed of. They're like combinations of water, methane, and ammonia, not necessarily in stoichiometric ratios, which these are kind of like the foundation of planetary ices. And, you know, the hope is that we can learn what these ices do and how they behave at planetary interior conditions, and then connect that to geophysical properties of the ice giant planets, things like magnetic fields, heat flow, etc. So specifically, I've been studying the superionic properties of these materials. So just to define this again, this is when you have a lattice of the heavy elements. So here you have oxygen in red and nitrogen in blue that will vibrate around their original positions, but not diffuse. Versus the white atoms, the protons, will diffuse like a liquid through the lattice. And so here the kind of white bars is tracing where the protons have been. So you can see that they do start to move significantly through the lattice over time. And so this occurs like in the temperature range between the solid phase when nothing is moving and the liquid phase when everything is moving. You might be wondering, like, why do these states form? Like, why would protons diffuse when the rest of the structure stays solid? And I should mention that we do, like, this has been observed for other elements too, like helium, lithium, also do this much more at like room temperature and pressure. Like I think a lot of solid state batteries involve superionic lithium. And even silver, which we think of as like much heavier element, has done this in compounds with iodide. So the simple answer is that protons have enough energy to escape their bonds with the heavier elements, whereas the heavier elements do not have enough energy to escape. So we can think of all atoms living in what we might call like a potential energy well. Like they're in their most stable position, and to move too far in any direction would take a lot of energy. But so all atoms will have the same amount of kinetic energy. And it turns out that protons require less to be able to escape their potential energy well. Firstly, they have a lower charge, so they have like weaker bonds. Secondly, they are lighter, like they're less heavy, they have smaller nuclei. And so it's easier for them to find like this middle position to be able to squeeze through heavier atoms without being grabbed by a really strong bond. And I should say this is much more complicated mechanistically than I'm getting into now. It's still a very active area of research, as I said, because superionic materials can make very good like solid state batteries. So there's a lot of other factors like volume, bond angle. This is kind of a simple overview. So a few of our findings. So I've run simulations like this on quite a number of high pressure hydrogen bearing materials. I think something like 15 HCNO compounds and maybe a dozen nitrogen hydrides. And so we've had a couple of really interesting findings. The first one, we are pretty excited to see that like quite literally all planetary ices at high enough pressures and temperatures will have a superionic phase. And so this is relevant back to the planets because many of these materials have superionic phases that are coincident in temperature and pressure with the interiors of ice giant planets. And so like one popular theory that this bottom non-convecting ice layer of Uranus and Neptune is that it's dominated by superionic materials because they're solid enough that they don't convect, but they're liquid enough that they carry charge, and maybe this charge motion in the bottom part of the planet kind of helps stabilize the convection in the upper part. And so finding that all of these hydrogen-bearing ices are superionic at these high pressures supports the theory that, you know, the deep interiors of these planets may be dominated by superionic materials. So another interesting finding that we had is that the more hydrogen atoms the structure has, the lower the temperature at which it becomes superionic. And so our theory here is that the more protons there are, the less interaction with heavy atoms that the protons will have. And so they have less strongly formed bonds, and there's also more room for them to move. So this is our theory here. This is a figure from my paper that's under review. And then another really interesting thing was that like repeatedly through experiments, it's been shown that hydrocarbons under high enough pressure and temperature will form diamonds. And there's this theory of like a diamond rain deep inside the ice giant planets, which is implicated in like different heat flows and luminosities of the planets. But we found, we believe for the first time, that carbon-bearing compounds, if they also have oxygen and nitrogen, the carbon is stable, it doesn't decompose into diamond. So that's a little bit interesting. We'll have to see if the experimentalists also find this to be true, or if this is one of the scenarios in which we just can't run the simulation for long enough or big enough to actually see what happens. So yes, we have our first paper about this under review right now, which is exciting. The undergrads in the room, of which I think there's one, this basically means we write up our best paper and we're very proud of it, and then we give it to people who don't know us and who we don't know. Well, realistically, we probably both know each other, but it's completely anonymous. And they give us back, their hopefully nice comments about what we need to change to make it actually publishable. So that's what I've been doing all semester. So yeah, I'm only at the end of my first year of the PhD. So I'm hoping throughout the rest of my PhD to study more about planetary ices and other transport properties therein, like viscosity, thermal conductivity, electrical conductivity, because I'd really like to, by the end of my PhD, be able to correlate this in some way, like heat flow or magnetic field generation, like overall geophysical properties of the planet. And apparently I'm not the only person who thinks Uranus and Neptune are interesting. So every 10 years, the planetary science community completes what's called a decadal survey. So this is a survey in which scientists from all over the world can contribute their ideas to what they think is important for the community to focus on next, including offering suggestions for what space agencies should focus on. So the planetary science community's most recent decadal survey was finished last year. And pretty overwhelmingly, the community wanted to see Uranus and Neptune studied more. And this is good because like in the last 15 years, I mean, Mars has gotten so much attention like forever, which is awesome. But in like the last 15 years, Jupiter and Saturn have also been studied in great depth. Like Juno mission, still ongoing. Cassini mission went on for a number of years. Like ESA just launched JUICE, the Jupiter Icy Moon Explorer, which is going to go check out like Europa, Callisto, and Ganymede. And then at the same time, NASA is about to launch Europa Clipper. So like Jupiter is getting a ton of attention. So it's cool that Uranus is going to be the next big frontier. So here's a breakdown of a few of NASA's most recent flagship missions. So again, you'll recognize Curiosity and Perseverance. Europa Clipper is going to launch soon. And so the Uranus orbiter and probe expected to launch in 2031. After it's launched, it will probably take something like 10 to 15 years to actually get to Uranus. So it'll probably be something like 2045 to 2050 before we get any data back from this mission. So maybe we should train our kids to be planetary scientists. This is the plan. And they're expected to spend about 4.2 billion on this. And so here's what they think, here's what people right now suggest the mission looks like. So first, it would have an orbiter. So hopefully it would orbit the planet for a number of years, collecting tons of data. And then it will likely also include a probe, which will drop into the atmosphere, study things like density, composition, temperature, pressure, probably other things I'm not thinking of. And then unfortunately, probes only get to make like one descent. And then eventually they get deep enough where it's hot and pressurized enough that they melt or do what they do. But so I'm quite excited to see this happen. I'm excited that this is happening in our lifetimes. It feels to me like maybe we're starting to get more space missions going on in like the last decade than we had in the one before that. It was a cool time to be in planetary science. Alrighty, that's all I had for you. Thank you so much.
Any questions for us?
The machine learning, how you make sure that it actually finds the relevant physical mechanisms that's happening in that area. So like, how is it machine learning will encode the sort of boundary conditions that you're expected to? Like now you're course grading stuff, I'm sure it's possible, but just like, I guess I'm just saying like, how it's gonna encode all the information that, like, I'm to speed up your processing time by just making assertions, right, about like past patterns.
Okay, I see what you mean.
In a better way than I said.
So I think what I'm being asked right now is how do we actually ensure the accuracy of machine learning potentials across different types of like atomic and molecular interactions that we're actually accurately representing chemical behavior. So I think the primary way of doing this is to make sure that your machine learning potential is trained on any like phase transition or significant chemical interaction behavior that you would like the machine learning potential to be able to recreate. The idea is if it sees enough data of a certain type of interaction happening, then it should be able to understand what happens when atoms and molecules interact in that way, which is basically based on their distances and relative angles and things like that. So I think that's the first rule, is make sure that you've trained on like every transition or like interesting thing you would like to see happening. The other thing is that you want to train it far past the boundaries at which you want to run it. So for example, you can't train it up to like 5,000 Kelvin and then try and use it at 5,000 Kelvin, because it's much better at inferring slightly lower temperatures and pressures than you've actually trained it on, because like it's possible at these higher temperatures and pressures that there's things happening in our much faster, more extensive molecular dynamic simulations that has been sampled from our like DFT-MD simulations. And I think also training it on like the higher temperatures and pressures then you want to use trains it on. I think you're more likely to see interesting chemical behavior at the higher temperatures and pressures, so that if it happens to occur at lower ones, it knows what to do.
You still have to like probe it if you're at the simulation at some point, but then you can use whatever the results of that is to train and then hopefully predict in the future.
What do you mean probe it?
Like, because you're saying that you have to have some sort of database to be able to train it.
Oh, absolutely.
So you're still like, yeah, so you still like have to run, but you can run them for smaller periods of time, and then you can extract them further.
Exactly. And so also for like atomistic simulation type machine learning potentials, you have to often go through a series of trainings. Like the first one might not be very good just based on your like DFT-MD data, because again, this was like a much smaller data set than you could use if you had a good machine learning potential. And so you basically would like train your machine learning potential and then run molecular dynamics, which basically means like seeing how the atoms move in real time. And you can check things like, how does the energy compare to DFT? How do the forces compare? And often the first iteration is not very good. So then you can take what we call like configurations or like snapshots of atoms that the machine learning potential did not do very well on, and like retrain them with DFT. Be like, for this configuration of atoms, let's get a really accurate understanding of what's happening and add it back to the data set. And so doing this iteratively over time and monitoring how things like, very basically like energy and forces work, but then you can also look at like really specific material properties that you're interested in replicating, like diffusion, phonons. So one would not stop until at all of the conditions that you want to replicate, everything looks very, 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 very well matched. No.
So if you were to go, it's really refreshing to see like the big picture and overview of like that big picture planetary science questions, machine learning and I have a really simple question. Did you ever see, kind of connected to the previous question, something weird happening in your runs with machine learning? That somewhere where your machine learning would predict something that you never saw in your DFT simulation. So, like what happens when you try to build, you get like the extrapolation that is like way off from the trend.
Yeah, that's a great question. What I was just asked is, with the machine learning potentials, did we ever see anything that was clearly non-physical based on our understanding of the density functional theory simulations? And the answer is yes, and that is like a classic signal that the machine learning potential has not been trained well. So like one really common issue I had when I first started doing this was at high enough temperatures and pressures. You would get like groups of atoms like suddenly clump together really tightly and form like these really big balls. That's totally non-physical. And that was actually because of the issue I was talking about before. You have to train it at higher temperatures and pressures than you actually want to use it, because in that case, it didn't understand what to do when the atoms got too close together. And so when they got too close together, it thought it was an attractive force instead of a repulsive force. So that's like the perfect example for why you have to have these conscientious training decisions. Hi, Jiju.
One simple question is the bipolar, a non-bipolar magnetic field.
Mm-hmm.
We see magnetic field, it doesn't align well with the state taking access of the that which are not that qualified.
I'm gonna just find the photo from you. So it means two things. So yes, firstly, we typically expect magnetic fields to have the magnetic pole roughly aligned with like the rotation axis of the planet. So for Earth, it's only offset by like a handful of degrees. So Uranus and Neptune, I think foremost, like dipolar means that there's only two poles. So like it's a very natural motion north to south. When it's quadrupolar, that means there's kind of like four nodes in which magnetic field lines move in and out. And so it's not quite as natural to associate this with like rotation axes, which like very naturally have two poles.
That's due to the convection of ice or some special compounds that environment, some X3 or new compound.
So I think what you're asking me is why do Uranus and Neptune have these weird magnetic fields? Yeah, so I think that the best guess is because of this proposed internal structure in which instead of having convection deep in the planet, which does result in a dipolar field, you would only have convection in like this thin upper layer. So like Sabine Stanley has done a handful of papers on this, and she's able to model that. I mean, I think you should recognize this image. This was from one of our group meetings. This is Sabine Stanley's grad student. A number of the different models that they've tried are able to roughly replicate the behavior of Uranus and Neptune's magnetic fields using like this layering and convection scheme. This layer? Oh, so that's a question, right? I think based on temperature and pressure, one would assume that any ices in there would be superionic. So I think that like, if you have like stably stratified conducting liquids, or maybe it's conducting solids. I think it's that. I think if you have a conducting solid in this layer, then you still get the same magnetic field. But then there's the question of like superionic materials, we think based on temperature and pressure should exist here, but they're kind of a mix between solid and liquid. It's a bit unclear like exactly how like the liquid portion would respond to the magnetic field or contribute. So I think this is one of the questions that I would like to try answer, maybe doing another project with like a geodynamo professor.
So from all the materials you should be seeing, which ones you expect to exist in your Neptune, like based on that composition?
Let's see, I can show you this. I don't remember off the top of my head which ones specifically were coincident with the isotopes, but it was something like 4 or 5 of them out of this list. So I think like a random grouping of high pressure. These were all found from a structure search, which is basically when like research groups use density functional theory to try and identify the most stable compounds within a certain chemical space. And so there were a couple of recent papers that tried to find novel compounds in the HGNO space. And so these were all the ones they came up with. But I think it was something like a third of the HGNO compounds that were suggested at like planetary interior pressures would have superionic phases like coincident with the isentrope, which is like the temperature pressure line of a planet's interior. But I don't remember which ones off the top of my head.